This presentation is on quantitative data and how to present it. So here I have a quantitative data set where quantitative data is numerical. So notice all my data here consists of numbers. Now numerical data can be thought of measurements to any degree. So these are measurements, they're length measurements, but these are just rounded off to the nearest whole number. So if I had wanted to, though, I could have rounded them off to a decimal. So quantitative data is numerical. It consists of measurements to any degree of precision, so it could just be integers if you want to round it off to whole numbers. And probably the best visual way of presenting this data is in frequency tables and histograms. So I'm going to show you how to do that using this sample data set, which represents the lengths of movies in minutes. So all these here are the lengths of movies in minutes. So one of the first things that you would like to do is sort your data. That means have it in order. And you can either sort it from smallest to largest or largest to smallest. So up here on the top you'll see the Data tab, and over here you see the sort commands. So A to Z is sorting it from largest to smallest or ascending order, and Z to A is sorting it from smallest to largest or descending order. I'm going to sort mine ascending, so what I need to do is highlight my data here, and notice I have 50 pieces of data, so it goes from A2 to A51 because I have a label, the length here, and I'm going to sort my data ascending, and notice as soon as I click it I immediately have my data all in order. Now we want to present this data first in a frequency table, and then from the frequency table we'll construct a histogram. So a frequency table consists of two columns. One column consists of classes, or they're basically ranges of values for the data, and then the frequencies are how many data values fall within each class. So I'm going to show you how we find these classes. It's important to keep in mind, though, that there is no one correct frequency table. Different people can construct different frequency tables. There is some subjectivity in values you pick, as you'll see when we go through this. Now, the first thing we want to do is decide how many classes we are. So notice the lengths here have been divided into different pieces, different intervals, and each of these intervals is referred to as a class. So we want to know how many should we have. A general rule of thumb is the number of classes will be usually between 5 and 20, where the smallest number of classes would be 5. Anything smaller isn't really going to give you much information. And anything greater than 20, again, is going to be too many. So what works best for the human eye and understanding is between 5 and 20 classes. Now, you could just subjectively, randomly pick a number of classes, or you can use something called Sturge's formula. Sturge's formula says that the ideal number of classes can be found by computing 1 plus the common log of the sample size divided by the common log of 2. Now, notice that 1 over the log of 2 can be computed and rounded off. So 1 over, and we'll go to formulas here. If I start typing in log, notice this drop-down menu, log 10, that's the common log. I'll double-click on it. Common log of 2, and we see that 1 divided by log of 2 is roughly 3.3. So an alternative version of Sturge's law is 1 plus 3.3 times the common log of the sample size. Here we're going to denote the number of classes with k, and we'll use this version of Sturge's formula to compute the ideal number of classes for our particular sample size. So we'll do equals 1 plus 3.3 times the common log, so that's log base 10, of 50. Our sample size is 50. And that gives me 7. Now it's not exactly 7. I actually rounded this off because I want to round to the nearest integer, and I simply, over here in number, you can increase or decrease the number of decimal places. I set it so it gives me an integer. So this says the ideal number of classes is 7, and that is why I have 7 classes in the frequency table I constructed. Now, once we have the number of classes, we need to figure out how wide we should make these intervals. So we need to find what's referred to as the class width. Now, it turns out that the class width is not the distance between these two endpoints on the intervals, where these endpoints of the classes are referred to as the lower limit and upper limit, respectively. It turns out that the class width is actually the distance between consecutive lower limits or consecutive upper limits. All right? Now, to find the class width, then, we're going to divide the range of the data by the number of classes. So remember, the range is found by taking the difference between the maximum value and the minimum data value. So equals parenthesis, because I want the difference to be computed before the division. My maximum data value, since I've had it sorted, is here, 162. And I'm going to subtract from that the minimum data value, which is here, the 83. Close a parenthesis so the subtraction is performed before the dividing, and then we're going to divide by the desired number of classes, which is 7, and that gives me 11.286. Now, with the class width, to make sure that you actually create the correct number of classes, you always should round this up. So even though this is close to 11, since it's a little more than 11, we're going to use 12 as our class width. Now, you don't have to round up to the nearest integer. Depending on the data, you might round up to the nearest tenth or hundredths if you have really precise data. Or you might decide that instead of 12, you would rather round it up to, say, 15. So you do have some choices on how much you round up your class width. I thought that 12 would be perfect for my data, so I just rounded it up to 12. So now that I have the class width, I can start constructing my lower class limits, and I need to first choose the first lower class limit, so the smallest class limit. Now, my smallest data value is 83, so my lower class limit cannot be larger than 83. It has to be at 83 or less. So I can either just use the 83, my smallest data value, or I could use something smaller. So for example, if I preferred nice round numbers, say 80, I might want to use 80. I'm just going to use the smallest data value though and use the 83. Now to construct the rest of the lower class limits, I know my class width is 12, so I simply add 12 consecutively until I get all my lower class limits. So what I'm going to do here is my next lower class limit will be equal to the 83 plus the 12. And now I can just copy and paste, and here are all my lower class limits. So that's how I got the 83, 95, 107, 119, 131, 143, 155. I added 12 consecutively to those. Now once you have the lower class limits, you can simply fill in your upper class limits. Notice that the next class starts at 95. The second class starts at 95. Since I'm only working with integers, then that means I can have the upper limit for my first class just be 94. All right? Now again, if I continue in that manner, the difference between upper class limits will also be 12, right? Because if I say, oh, I'm going to start the third class at 107, I have to end the second class at 106, and notice there's simply a difference of 12. So I can find all my upper class limits the same way I did my lower class limits by simply taking one of the smaller class limits, like the first one, or in this case I'm using the second, adding 12 to it, copying and pasting the formula, and it fills in all my upper class limits. So here's all the upper class limits. Alright, so this is how I got my classes. My first class goes from 83 to 94, my second from 95 to 106, and so on. So down here, I just simply cleaned it up a little and wrote the classes all together as an interval of 83 to 94. And this would be inclusive. I now need to find how many of the data values fall within each of these classes, and so that would be the frequency of the class. I could physically count through these, right? 83 to 94, let's see, 83 to 94, that's these first 7 values, so my frequency would be 7. So I could count that way, or I could have Excel do it for me. So what Excel does then is if you go to your Data tab and your Data Analysis add-in, Actually, to help you construct a frequency table, you go to histogram. So when you click on data analysis histogram, it actually doesn't give you a histogram. It gives you the frequency table from which you could construct a histogram. So I click histogram from the data analysis tool. Okay. And now I have to give it the input range. All right. So let me go ahead and clear these out and show you how I select them. So my input range, see here, I'm going to include my label because then that will label my table, frequency table. Highlight everything from A1 to A51. Oops, wrong place. My input range is here. So I want to highlight again from A1 to A51 because I'm including my label. I need to make sure Excel knows I'm including my label, so here you make sure the labels box is selected. And then I need a bin range. And what the bins are basically the cutoff point so it knows when to start counting for a new class. So the cutoff points will be the upper class limits. So that's why I have here upper class limits or bins. These are the bins. So I'm going to go ahead and select these. I have labels, so I went ahead and selected upper class limit there as well to tell it I have labels. And now I need to tell it where to put the output. Usually you can put it in a new worksheet. I know exactly how big this output's going to be, so I'm going to highlight where I want my little frequency table to go. So there's my output range. And now I simply click OK, and here it is. So notice, because I entered the labels, I have my upper class limit as the bins. And here are all those upper class limits and the associated frequencies. Notice there's that 7 that we counted ourselves. Okay, so it fills in all the associated frequencies. Notice what Excel does though is it adds this last class, which is basically more. And if we do our tables so they're nice and finite and inclusive, we won't really worry about this. But Excel always adds this more class that we're never going to use. We are not going to use, and it's best if you don't use a open-ended class like that. Alright, so here is a frequency table that we could use to construct a histogram. However, that histogram would give us the upper class limits as the labels, and I prefer to do something else. So I am going to go ahead and fill in my own frequency table here. And I'm just going to copy the frequencies that Excel found for me. So I will copy these and paste them. So here are my frequencies. And I want to construct a relative frequency column. So we know that relative frequencies is simply your frequency divided by the sum of the frequencies. Now remember, the sum of these frequencies was 50 because I had 50 data points. But just to confirm that, let's go to Formulas, Auto Sum, and I'll hit Enter, and see, and I do have my 50 values. So now for my relative frequency, I'm simply going to divide each of these frequencies by the total 50. And again, because I used the formula, I can copy and paste, and here are all the frequencies. Right? This one I want to have to the same number of decimal places. So I'm actually going to go to Home and increase the number of data places so they're all to 2 places. All right? Now I want percent. There's different ways of doing this. I actually just do the formula with my relative frequency times 100, though I believe you can also use a percent symbol. So now that I have that formula, I will just copy and paste that. So that's done. Oh, let's go ahead and show that the sum of our relative frequencies is 1. So Formulas, Auto Sum, there's the 1. Notice it also gave me here, there's the sum of my percents. Okay. Alright then. Now I have my frequencies, my relative frequencies, my percent frequencies, my classes. I'm ready to construct, almost ready to construct a histogram. But the preferred method of labeling the bars in a histogram are not with the entire interval range, not with just an upper limit or a lower limit, but with what we call a class midpoint. And that's a class midpoint's exactly what it sounds like. It's the midpoint of each class. So to get a class midpoint, you're going to add your lower limit with your upper limit, take that sum and divide it by 2, and that'll give you the midpoint. So the midpoint of the first class is 88.5, and again, since I used the formula, I am just going to copy and paste all the class midpoints. So it's these class midpoints here that I want to use to label my histogram. So this will be the horizontal or x-axis will be the class points, and my vertical axis or y-axis can be either the frequencies, the relative frequencies, or the percent frequencies. You will actually get the exact same looking graph for each of these. Of course, just the numbers will be labeled slightly differently. I think I'm going to work with the relative frequencies. So what you want to do then is highlight your output. So I'm highlighting relative frequency, and I want to insert then a histogram. So remember, we go to column and we just select a 2D column chart. It's the same command for a bar chart, but now we're doing the histogram. And here's what Excel automatically makes for me. Now, I want a histogram, and remember on these styles you actually have the histogram option where the gap has been made 0, the gap between the bars. So I'll just click on that. I personally don't like all my bars run in together like this. I like to see the outline of the bars. So I'm going to right click and go to Format Data Series. Notice, see the no gap here. If you had a gap, you would select this, take this down to 0. And I want a border that is a solid line. I'm going to make it black. And now I actually can see my individual bars. So that's just my personal preference. That's not absolutely necessary. What is necessary, however, is to get the correct labels on my horizontal axis. Now remember, my horizontal axis, I want to be the class midpoint, so I can just click and type. There are my class midpoints. So what I need to do is right click and select data. It's the horizontal axis I need to change, so I will edit that. And now I will highlight my data, my class midpoints. Boom, highlight all those, click OK. See, there they are now. OK, and now I have my class midpoints on the horizontal axis. My vertical axis, remember, is a relative frequency, so let me go ahead and type that in. Okay, so there's my relative frequency. Notice my title is based on the label from the y-axis, but I'm going to call this lengths of movies. Or let's just say movie lengths. Movie lengths, and I'll just put minutes. Oh, if it's relative frequency, yeah, we'll put minutes. Well, the class midpoints are minutes. I'll just put it up here so they know that those class midpoints are in minutes. So here we go. And here is my frequency table. And up here, notice in design, you got all these fancy designs. So if you wanted to make it fancy, you could choose an option. The 3D options are nice. Some people like the black background, so you could make it look like this. Alright, so here we go then. Here's a nice frequency table, histogram from this nice frequency table. And what I did is I used the histogram command to form this frequency table that helped me find the frequency so I didn't have to do them by hand. So here now what I've created is a summary of my data. I've summarized the data in an easily digestible format, and I've even taken the frequencies and made it a visual graphical picture so you can see the distribution, which looks skewed, right? Looks a little skewed. We got a little tail hanging off here. So basically a skewed data, though probably not too far from the bell curve that we could still use certain analyses, because we still have kind of a low, high, low, though this goes really low. And if your data is not too far from bell-shaped, it's actually quite a weak requirement. You can have a bit of flexibility. We can do some further analyses on this that we discuss in the next lesson. But let's now look at finding our summary statistics for this data. Now, to find summary statistics, we're going to use the Descriptive Statistics command from our data analysis tool. So data, over here in data analysis, there is a Descriptive Statistics command. And in that Descriptive Statistics command, you will end up checking Summary Statistics box. You want a Summary Statistics box. So if I click OK, And let's clear all this so I can show you where it comes from. But right here, notice here are the summary stats. So you would click that summary stats box. All right. And then the output, usually we put it in a new worksheet. I'll go ahead and put it in yet another worksheet called Sum Stats, different from this one I'm working on, so you can see when I do it. So notice, from what I've done previously, I got this output. There are some blanks here because I deleted the things we're not interested in. So let me first discuss what this output is, and then we'll go back and actually find it again. So here are the lengths, and so the mean, which is the average length, is 116.9. Notice I have it rounded to a single decimal place because the general rule is you round sample statistics to one more decimal place than your original data. So original data was all in integers, so I rounded to the tenths. All right? So this is our mean, which is one of our measures of central tendency. All right? So a measure of central tendency is a way of measuring the middle. Right? It's a way of measuring the middle of our data, and the mean is just an average. Recall from when we studied probability, the mean is the arithmetic mean, and it just represents an average, which means add up all the data, divide by how many you have. So that's what the mean is here. It's the average that we're all used to. All right. Now there are other ways of measuring the middle, and one of them is the median. So here is the median in our data set. It turned out to be 118.5, and the median is actually the physical middle of the data set. So that means if I go over here to my data set and I go down to the middle, which would be around the 25th, and remember this is it starts at A2 and goes to A51. It actually has two middles, and since we started at A1, it would be the 26th and 27th. These are our two middle pieces of data. So this doesn't have a single physical middle. So the median would be a physical middle, so either a single value, or if you have an even number of data values, it'd be the average of these two middle values. So that, notice, between 118 and 119, 118.5, that's where this comes from. Okay, so that's the physical middle, which happens to be the average of the two middle data values when you have an even number of data values. Now the mode here, 127, that's the most repeated data value. Now with Excel, it could be that you actually have more than one mode. It is possible for data to have more than one mode, which means more than one data value can be repeated the most number of times. So you might, like maybe 127 occurs 5 times, but I also have something else that occurs 5 times, but nothing else that occurs more than that. Excel will only give you the first repeated value, the first mode. So you really need to glance through your data and see if it has a single mode. But that's our most repeated data value. So let's go to our ranked data. It said that 127 is our mode, so we know that if there's more than one, that would be the first. And we see 1, 2, 3, 4, 5. See, we have 5 127s. Does anything else repeat as many times as that? No. So it does have a unique mode of 127. But you should check and see if it's multimodal. It's also possible to have no mode. So there are times where if none of your data values repeat at all, you have no mode. If you have 2 repeats, then it would be bimodal, if you just have 2 repeated the same number of times. Otherwise, more than 2 repeats would be multimodal. And that's repeated the same maximum number of times. We've talked about standard deviation and variance before. So remember, the variance is the square of your standard deviation, or you can think of the standard deviation as the square root of the variance. Okay, they are related. Now, the standard deviation, we probably should talk more about. There's a lot that can be said about the standard deviation. The standard deviation is a way of measuring the spread of your data. All right, it's a way of measuring the spread of your data. And it's a way of measuring the spread that takes into account every single data value, and it's actually going to be in the same units as the original data. Okay, so it's in the same units as the original data. Well, you're thinking that's good. Why wouldn't it be? And it wouldn't be if I explained what the variance is and why we would use a variance. But for now, let me just say that the standard deviation is the most desired measure of spread or variation of your data. It's in the same units as the original data, so comparing standard deviations with your original data makes sense. Notice that your variance is the standard deviation squared, so variance isn't actually squared units, which is not as useful. Range, we've talked before, that's the max minus min, right? Range is max minus min, so this is a nice quick measure of variation. Okay, here it's 79, which you can see is the 162 minus the 83 gives you the 79. So it's a nice quick way of measuring the spread, but it only takes the extreme values into account, right? So we don't really get a full picture of what's happening in between the extreme values, whereas the standard deviation gives us a complete picture of what's happening between those extreme values. So I'm going to talk more about that in a moment. And then the last thing I have down here is the count. This is just your sample size, okay? That's your sample size n. So that then reminds us how many pieces of data we had, or you can think of it as a confirmation that you did indeed have all your data evaluated when you were doing your summary statistics. So if this doesn't match your sample size, you know that there's a mistake someplace. So that's why I like to look at it as a quick confirmation that I got all my data in there. Alright, so let me go ahead and show you how to construct this, and then I'll spend more time talking about the standard deviation and the variance. So to construct the summary statistics, as I said, we go to the Descriptive Statistics command and the Data Analysis menu, and then within the Descriptive Statistics tool, we make sure that we tell it to compute summary statistics. So we go to Data Analysis here, and right, there's the Descriptive Statistics. Okay, my input is of course going to be my data set. Doesn't matter if it's raw or sorted. So I'll just go to the raw data to show you. So I'm going to highlight all my raw data, including the label again. So make sure that you tell it you have labels. Okay. So I'm also in columns, and I'm just going to put it in a new worksheet, some stats. Oh, but don't forget to tell it to compute those summary stats. You can also have it compute a margin of error for your confidence level, which we will be talking about in another presentation. So now I'm going to click OK. We go right to our new page, Summary Stats, our new workbook. I'll double click there so we can see. And here we have our label here, so there's the length. So we got that now up here, and now we can see here's our mean. Notice that it gives us all kinds of decimal places. I said we really want to round to one more decimal place in the original data, so that's why I actually decreased the number of decimal places to 1 on these things. Okay, so here's our 116.9 for the mean. Alright. Here's our 118.5 for the median. Here's our mode of 127. Here's our standard deviation. Let's decrease these decimals. So about 17.5 is our standard deviation. Right? Here's the sample variance, which is the standard deviation squared. Right? So there's the sample variance. So notice this is the standard deviation squared, right? I told you equals standard deviation squared. Oops, let's take rid of that. That's the standard deviation squared, so I can actually go equal standard deviation squared, see? And there it is, the 307.1. Okay. We're not gonna worry about kurtosis and skewness. Alright. Here's the range of 79, which was computed using the maximum 162 minus the minimum of 83. The sum of our data values, we're not interested in that, so I'll just take that away. And then here's the count of 50 as the double check. Alright? Okay, so standard deviation. What do we mean by standard deviation? How does it use to measure all the data? All right? And in the next lesson, I'll actually address what the standard error is. I'll do that in the next lesson. So for now, I'll get rid of this, but we'll look at the standard error in the next lesson. Okay, so the standard deviation. All right, the standard deviation, I told you, is a measure of the spread of the data. And it takes every data value into account. So what the standard deviation does, if I were working for a population, so let's first think about population, the population parameter, all right, for the standard deviation. What I want to do is basically look at, I'm interested in basically an average difference from the mean. That's what I'm interested in, is an average distance from the mean. Now, if I were to actually just go, okay, well, let's take our data value, let's subtract from it the mean, okay, and here is a distance from the mean. Now, if I always do it in the same order, x minus mean, we know that some of the data values are less than the mean, so this difference would be negative. Some of the data values are above the mean, so that difference would be positive. But since the mean, remember from our discussion on probability, is like a balance point and is the middle, these pluses and these minuses, this negative and positive differences, when I add them all up, the sum of all these would actually equal 0, and that would not be useful for us. So we cannot have these both positive and negative. So the question is, how can you make things positive? Well, one of the ways is actually to take an absolute value, right? You may recall absolute values are distances from 0, so I could take the absolute value of the difference between x and the mean, and then everything would be positive. Now, sometimes that is done, and it's referred to as the mean absolute deviation. So MAD stands for mean absolute deviation, which works with absolute values. So what you would do then is you would take the sum of the absolute values of those differences, and then you would divide by how many you had, because then that would give you an average, right? That would give you the average. Okay, however, absolute values do not have great mathematical properties. This is not really the best mathematical way of doing it. There's another way. So that other way is the standard deviation. And so what the standard deviation does to average out the differences of the means is it will, to make the sum positive, it will actually square these. So down here, what that standard deviation does to make all these numbers positive, it squares the differences. Okay, it squares the differences here. So now when you sum it up, you do not get 0. When you sum this up now, you're going to get something greater than 0. All right, so that is good. That is meaningful. We'll get something greater than 0. Okay, well, this is just a sum of squared differences. It's not an average. What we need to do then is divide this sum by the number of data values we have. Okay, so we're going to divide this by the number of data values, which if it was for a population would be big N. Okay, so we're going to divide the sum by N. But then we're in squared units, right? This actually is your variance right here. What I have found here is your variance. Okay, so that's why the variance is in squared units. I want to get it in the original units, so what I have to do then is I have to take the square root of this here. Okay, so let's just copy this. Oh, it didn't work. Okay, so I'm going to take the square root of the sum of the squared differences between the values in the mean and its average was divided by big N. Okay? Alright, so the square root of the sum. So notice then, I forgot to divide. Alright, I mean to close a parenthesis. So the square root of a sum, okay, of the squared differences, and then it's divided by n, so we have an average of the squared differences and then the square root, and that gives us the standard deviation. But what I've shown you here is the population parameter. That's the population standard deviation. So what we have right here is for a population. We're interested in samples. Now with samples, instead of dividing by n, with the sample standard deviation, which we usually just denote as S, okay, or you can just call it SD, and it's understood that it's a sample. For a sample standard deviation, alright, what you want to do is instead of dividing by n, you're going to divide by what we call the number of degrees of freedom, or df, and the degrees of freedom is going to be 1 less than the sample size. So n minus 1. 1 less than the sample size are the degrees of freedom. Let's make this bigger. Okay? Alright, so 1 less than the sample size, n minus 1, that's the degrees of freedom. And this will make our statistic, this makes the standard deviation what we call consistent and unbiased. Okay, so this makes the standard deviation consistent and unbiased. So the actual formula that you will see for a sample standard deviation is the square root of the sum of the square differences between the mean, but then what we have to do is divide by n minus 1. Alright, and that's the only difference. Okay, so I will make a presentation that just talks about standard deviation while I will review all of this. Right now, just know that is the desired measure of variation that you use using your summary stats. And that concludes this presentation.